Okay, quick video on electromagnetic radiation, should be a review, but just in case you weren't paying attention or were absent those days. So this is the spectrum of electromagnetic radiation. You go from very, very, very high frequency, short wavelength gamma rays to short, low frequency, very long wavelength radio waves. The part that we can see, visible light, is right here in the middle, and if you look at the entire spectrum, you see that what we see is actually very, very, very small portion of that. Okay, we use some vocabulary words. We had frequency and wavelength. We're going to define them. We'll start with frequency. Frequency is the number of cycles that happen in a unit of time, generally 1 second, and frequency looks like high frequency, looks like this. So between, let's say, 3 seconds and 4 seconds of time, 3 seconds and 4 seconds, the frequency would be how many of these waves actually pass by this point in that 1 second period of time. Okay, next we have wavelength, which shockingly is the length of waves. What that means is you take a wave and it's the distance between the crests of two waves. Let's just draw two waves real quick. Okay, we drew three, but the crests are the top, so you'd go here to, we're looking for the crest on the wave next to it, so that's the next wave, here's the crest, so the wavelength would be from this x to this x. Now, something with a shorter wavelength would be like this. Probably should have switched colors, that was my bad. But in this case, your wavelength is from here to here, much shorter than the other. Now, if you notice, increasing frequency points to the left, and increasing wavelength points to the right. That's purposeful. As frequency goes down, as frequency increases, increasing frequency, the wavelength increases going to the right. So going to the left means if frequency is going to the left and it's increasing, that wavelength has to be going down. So over here you have high frequency, very low wavelength. And over here we have very, again, high frequency, low wavelength. And then over here we have very high wavelength, but very low frequency. That's an inverse proportion. As one goes up, the other goes down. Now, speed of light is speed of light. Radio waves, microwaves, infrared, UV, visible, X-rays, gamma rays, they all travel at the same speed. 3.0 e to the 8th meters per second. Sometimes people will write it like this, 3.0 times 10 to the 8th meters per second. I prefer the E notation just because it's fewer things to write, but whatever you're comfortable with. That's why it's an inverse relationship. As frequency goes down, wavelength goes up. But your formula for speed is constant equals wavelength times frequency. Which means in order to stay constant, in order to stay the same, which it's right in the name, the speed of light is constant. If lambda goes up, your wavelength goes up, frequency has to go down to keep it equal. In class we used the examples. Let's pretend that the speed of light is actually 12, and we'll say that our lambda is 6 and our frequency is 2. Now the inverse proportion means that if wavelength goes down, frequency should go up. So to keep this equation equal, we're going to say 12 equals, now wavelength needs to go down, so let's say wavelength becomes a 3. Frequency should go up. Well, what times 3 equals 12? 4. So wavelength went down, 6 to 3. Frequency went up from 2 to 4. So if you need the real numbers, use the real numbers. Alright, and last thing, where it says wavelength, you have your lambda Our unit for wavelength is meters. The symbol for that is the lowercase m. And frequency, our unit is hertz. And our unit for that is big H, little z. Now, occasionally in problems, I'm not going to tell you, hey, this is the frequency, this is the wavelength. You need to be able to recognize it from the units. Hertz is a frequency, meters is a wavelength, and meters per second is speed. That one you should know from real life, things like miles per hour, feet per minute, things like that. Meters per second is speed.